In this section, we'll dive into some real-world applications of the encryption concepts that we've covered so far. In the last section, we mentioned SSL TLS when we were talking about digital certificates. Now that we understand how digital certificates function and the crucial roles CAs play, let's check out how that fits into securing web traffic via HTTPS. You've probably heard of HTTPS before, but do you know exactly what it is and how it's different from HTTP? Very simply, HTTPS is the secure version of HTTP, the Hypertext Transport Protocol. So how exactly does HTTPS protect us on the internet? HTTPS can also be called HTTP over SSL or TLS, since it's essentially encapsulating the HTTP traffic over an encrypted secured channel utilizing SSL or TLS. You might hear SSL and TLS used interchangeably, but SSL 3.0, the latest revision of SSL, was deprecated in 2015, and TLS 1.2 is the current recommended revision, with version 1.3 still in the works. Now, it's important to call out that TLS is actually independent of HTTPS and is actually a generic protocol to permit secure communications and authentication over a network. TLS is also used to secure other communications aside from web browsing, like VoIP calls, such as Skype or Hangouts, email, instant messaging, and even Wi-Fi network security. TLS grants us three things. 1. A secure communication line, which means data being transmitted is protected from potential eavesdroppers. 2. The ability to authenticate both parties communicating through typically only the server is authenticated by the client. And 3. The integrity of communications, meaning there are checks to ensure that messages aren't lost or altered in transit. TLS essentially provides a secure channel for an application to communicate with a service, but there must be a mechanism to establish this channel initially. This is what's referred to as a TLS handshake. I'm more of a high five person myself, but we can move on. The handshake process kicks off with a client establishing a connection with a TLS-enabled service, referred to in the protocol as client hello. This includes information about the client, like the version of the TLS that the client supports, a list of cipher suites that it supports, and maybe some additional TLS options. The server then responds with a server hello message, in which it selects the highest protocol version in common with the client and chooses a cipher suite from the list to use. It also transmits its digital certificate and a final server hello done message. The client would then validate the certificate that the server sent over to ensure that it's trusted and it's for the appropriate host name. Assuming the certificate checks out, the client then sends a client key exchange message. This is when the client chooses a key exchange mechanism to securely establish a shared secret with the server, which will be used with a symmetric encryption cipher to encrypt all further communications. The client also sends a changed cipher spec message indicating that it's switching to secure communications, now that it has all the information needed to begin communicating over the secure channel. This is followed by an encrypted finished message, which also serves to verify that the handshake completed successfully. The server replies with a change cipher spec and an encrypted finished message once the shared secret is received. Once complete, application data can begin to flow over the now secured channel. High five to that. The session key is the shared symmetric encryption key used in TLS sessions to encrypt data being sent back and forth. Since this key is derived from the public-private key, if the private key is compromised, there's potential for an attacker to decode all previously transmitted messages that were encoded using keys derived from this private key. To defend against this, there's a concept of forward secrecy. This is a property of a cryptographic system so that even in the event that the private key is compromised, the session keys are still safe. The SSH, or secure shell, is a secure network protocol that uses encryption to allow access to a network service over unsecured networks. Most commonly, you'll see SSH used for remote login to command line-based systems. But the protocol is super flexible and has provisions for allowing arbitrary network ports and traffic over those ports to be tunneled over the encrypted channel. It was originally designed as a secure replacement for the Telnet protocol and other unsecured remote login shell protocols like rlogin or rexec. It's very important that remote login and shell protocols use encryption. Otherwise, these services will be transmitting usernames and passwords, along with keystrokes and terminal output in plain text. This opens up the possibility for an eavesdropper to intercept credentials and keystrokes. Not good. SSH uses public key cryptography to authenticate the remote machine that the client is connecting to, and has provisions to allow user authentication via client certificates if desired. The SSH protocol is very flexible and modular and supports a wide variety of different key exchange mechanisms like Diffie-Hellman, along with a variety of symmetric encryption ciphers. It also supports a variety of authentication methods, including custom ones that you can write. When using public key authentication, a key pair is generated by the user who wants to authenticate. They then must distribute those public keys to all systems that they want to authenticate to using the key pair. When authenticating, SSH will ensure that the public key being presented matches the private key, which should never leave the user's possession. PGP stands for Pretty Good Privacy. How's that for a creative name? PGP is an encryption application that allows authentication of data along with privacy from third parties, relying upon asymmetric encryption to achieve this. It's most commonly used for encrypted email communication, but is also available as a full disk encryption solution or for encrypting arbitrary files, documents, or folders. PGP was developed by Phil Zimmermann in 1991, and it was freely available for anyone to use. The source code was even distributed along with the software. Zimmermann was an anti-nuclear activist, and political activism drove his development of the PGP encryption software to facilitate secure communications for other activists. PGP took off once released and found its way around the world, which wound up getting Zimmermann into hot water with the US federal government. At the time, US federal export regulations classified encryption technology that used keys larger than 40 bits in length as munitions. This meant that PGP was subject to similar restrictions as rockets, bombs, firearms, even nuclear weapons. PGP was designed to use keys no smaller than 128-bit, so it ran up against these export restrictions, and Zimmermann faced a federal investigation for the widespread distribution of his cryptographic software. Zimmermann took a creative approach to challenging these restrictions by publishing the source code in a hardcover printed book, which was made available widely. The idea was that the contents of the book should be protected by the First Amendment of the US Constitution. Pretty clever, huh? The investigation was eventually closed in 1996 without any charges being filed, and Zimmermann didn't even need to go to court. You can read more about why he developed PGP in the next reading. PGP is widely regarded as very secure, with no known mechanisms to break the encryption via cryptographic or computational means. It's been compared to military-grade encryption, and there are numerous cases of police and governments unable to recover data protected by PGP encryption. In these cases, law enforcement tend to resort to legal measure to force the handover of passwords or keys. Originally, PGP used the RSA algorithm, though that was eventually replaced with DSA to avoid issues with licensing.